So carrying on from the last lesson, talking about energy transformations, energy transfers and things like that, we're going to talk again about useful energy. As discussed so far, we've spoken about it already. When energy is used, some of it's useful and some of it's wasted. So here we have an example. We have an input energy, whether that's chemical potential, electrical energy, gravitational potential, whatever it is. So we have a certain amount which is useful energy. Ideally we want that to be as big as possible. In this case, we've got kinetic energy is considered to be the useful energy. So it could be anything that has motion. So useful energy could be a plane, could be a car, a boat, a fan, a ball being thrown through the air, anything like that. And we have a certain amount of wasted energy. Now, wasted energies generally come under these three main categories: heat, light and sound. They don't always have all three of those, but often they do, depending on what it is, particularly if it's a combustion engine. So we call this stuff wasted energy. It doesn't disappear. It still exists. Can't be created or destroyed. So this energy can't be destroyed. It just gets transformed. So here's some examples. What I want you to do is pause the video in a moment and go through, and I want you to put, you can just use HE for heat energy, EE for electrical energy, CPE for chemical potential energy. And look at the energy transformation that's occurring in each of these. There's a couple that have an energy transference as well. Talk about which one is useful energy and what is the wasted energy. What I've done is I've just included here the ones that are useful in this transformation or transference, and then we're just going to put the wasted ones there. So if you can do that now. So hopefully you've just done that. If you haven't, well, I guess you're probably, if you're finding it easy, or if you're finding it particularly difficult, maybe you needed to do this. But you're going to need to know how to write these down. So we've got the first two examples here. We've got the lawnmower. Now it uses fuel, so it's chemical potential energy. And we're doing that to get kinetic energy. Now the useful energy is the kinetic energy. However, we have heat energy and sound energy. They're our wasted forms of energy in this situation. We don't want the heat and we don't want the sound, and we all know that a lawnmower gets really hot and it also is incredibly noisy. So a wind turbine, we have kinetic energy of the wind. Now that kinetic energy transfers to become the kinetic energy of the wind turbine, and then we create electrical energy out of that. So the useful energy, we're going to call that electrical energy at the end. But the wasted energy, we're going to talk about the heat energy that's generated as the turbine spins, and the sound of the turbine. Like, they're reasonably loud, not loud compared to what they do, but you can still hear them from 50 meters or so away. Heat energy as well. When we've got the kinetic energy, so in the turbine, there is a bit of friction and creates heat energy. If you weren't sure what to do up to now, do the rest. So with an oven, we've got the chemical potential energy of the coal at the power station. That might be one that you missed. If you just went straight to electrical energy, that's okay. So we're burning coal, we're assuming this is coal-fired power station. If we had a wind turbine, like in Albany, driving the electrical production, we would actually just put kinetic energy instead of that. So we get the electrical energy which comes into your home. So what we want out of an oven is heat energy and kinetic energy. I'm put kinetic energy there because my oven's fan forced, so it has a fan in there which is also running off the electricity. Heat energy and kinetic energy are what I want. If you just got an oven that doesn't have a fan in it, you just have heat energy there. And the waste product is sound energy. Now I've put plus heat energy there because even though heat energy is a useful energy, if you've ever used an oven, you'll notice that, even up to hours afterwards, the oven is still hot. Now I'd consider that wasted energy to a certain extent. They're not particularly efficient, like the toaster I spoke about in one of the other ones. So light globe again, we're talking about the chemical potential energy at a coal-fired power station. You could put kinetic energy in there as well, instead of not as well. Well, actually as well, because some Some places run off both, essentially, if the wind generators aren't enough at that particular time of the day. They might be pulling off the grid, which is powered by coal. Or it could even be gravitational potential energy as well if you've got hydroelectricity. Or it could be kinetic energy if you're using wave energy. It could be light energy if you're using solar. Becoming electrical energy, and a light globe, what we want the light energy. So that's the useful energy here. You could argue that there is more heat energy produced than light energy in a light globe. Oh, at least the old incandescent ones. You've got less heat energy in the LED lights that we use now. In a microwave, we've got chemical potential energy. Again, that's the electricity coming. That could be kinetic if it's at wind powered, or it could be light if it's a solar one. And then we have electrical energy, comes into your home. Now this one's interesting. We get kinetic energy because that's the turntable. But in a microwave, the food is cooked by microwaves. Now, microwaves are a kind of electromagnetic radiation. They're actually a kind of light, but they're a kind of light that we can't see. It is light, and it's just like the colors that we see, the greens, the blues, the reds, the white light, the sunlight, all that sort of stuff. But we can see those, and that's called visible light. Microwaves are a kind of light that we can't see, like radio waves. They're like the waves that come from your mobile phone. So the useful energy that comes out of a microwave is the light energy and the kinetic energy. And there's a bit of sound, and that sound energy is wasted energy in a microwave. You could say that there's heat energy lost as well, like in a light globe, but not very, or in an oven, but not very much. A paper plane. We've got gravitational potential energy. It's above the ground. And we've got kinetic energy. So that is the energy of whoever's throwing it. You could argue that the kinetic energy of the person who's throwing it comes from chemical energy, because that's the energy they're using to do it. And then you could go all the way back to sunlight if you really wanted to. So the desired useful energy is kinetic. A little bit of heat energy is wasted. A bit of friction, really not very much, and a tiny little bit of sound energy. So you could argue that paper planes are pretty energy efficient. We have an electric toothbrush, chemical potential energy, or kinetic energy, or solar or light energy, whatever's producing the electricity, so electrical energy, and then kinetic energy is really what we want out of a toothbrush. Lots of sound energy, a little bit of heat energy in the motor that's running that vibration. And we've got a skydiver, so you've got gravitational potential energy to become kinetic energy. Useful energy is kinetic. Sounds strange. Kinetic energy rushing towards the ground. But anyway, that's what they want out of this experience. There's a reasonable amount of heat energy as you fall, moving through the air molecules, but also there's sound energy as that happens. The energy efficiency is a measure of how much the input energy is converted into useful as a percentage. So lots of wasted energy means that the thing isn't very efficient, because not much of the input energy is becoming useful energy. So nothing is 100% energy efficient. Nothing. Absolutely nothing. There's always energy wasted. So something is energy efficient if most of the input energy, or a large amount of the input energy, becomes a useful energy. So here we can see a human, we're only about 25% efficient. We produce a lot of heat as a waste product of the energy, the chemical potential energy in the food that we use. A power station, so that's a coal-fired power station. It's only 30% energy efficient. A steam engine, about 40% energy efficient, runs on, we're burning coal here, and we're also burning coal here, so a steam engine's a little bit more efficient than a coal-fired power station. Electric motor, very efficient, not much heat, not much sound energy from that. And here we go, the incandescent light bulb, 5%. Okay, a bit more than I thought. I thought most of the other 95% is pretty much heat energy. Tiny little bit of sound energy, they got a little buzz to them. But so yeah, 95% heat energy from an incandescent light globe. It's pretty much why we got rid of them and replaced them with little fluorescent ones, or LED, eventually after that, LED lights. Here's a question. In 5 minutes, a particular battery operated remote controlled car used 1800 joules of chemical energy. Out of that energy, 450 joules was kinetic, 300 joules became sound, 1050 joules became heat. So they add up to the input energy of 1800, those numbers there. The energy in a battery is actually chemical energy. There's a chemical reaction that occurs there, transforms that chemical energy into electrical energy, which the energy efficiency equation, useful energy divided by total energy, and we times it by 100 to make it a percentage. So in this case, we've got energy efficiency equals 450, that's the kinetic is what we want, into 1800 times 100. Oh, that's right. I've also put the useful energy would also be light, because if anyone's ever used a remote control battery operated car, it's got lights and flashing and all that sort of stuff often going on. So the efficiency is the 450 divided by the 1800. The 450 is the useful, 1800 is the total, times 100 to get it a percentage, and this one's 25%. Look at another question here. Jim mows. Jim's mowing. I'm sure that's a bit of a gag there. He is mowing grass in 2 minutes. Okay, so with the last question and this question, the amount of time doesn't matter. It's a red herring. So a red herring is when something, a bit of information is put in there to mislead you. The time taken would be important once you get to year 10 and you start doing how much work was done. But at this level, we don't need to worry about that. 3,200 kilojoules of chemical energy, and the kinetic energy is what we want, and so it's 800 kilojoules. 800 divided by 3,200 times 100 to get it as a percentage. Again, it's 25%. So I decided that question was boring. You got 2 questions in the textbook. You come out with the same answer. It's not always going to be 25%. Look at this. It's not always 25%. Right, some revision. 5 forms of energy that do work. 4 examples of potential energy. You want flow diagrams for these 2 scenarios. A plant growing is eaten by a horse, which then runs up a hill and falls down a cliff on the other side. There's a lot to that flow diagram, isn't there? If you're somebody who likes horses, you won't like that question very much. I put that question in there because one of my students was obsessed with horses, and I did it just to annoy them. A plane takes a skydiver from the ground into the sky. Skydiver jumps from a plane and falls to the ground, releasing the parachute on the way down. Okay, that's interesting. How's that going to make a difference? Do those questions now. So hopefully you've answered these questions. Let's go through some answers. So we've got the types of energy that can do work. Kinetic heat, light, sound, electrical energy, nuclear energy. Some of them can go in both categories, to be honest. Potential or stored energy, gravitational, chemical, electrical potential energy, and magnetic. Magnetic's one I hadn't mentioned in these videos, but I have just put it in. Sorry about that, but anyway, I was trying to find some more potential energies. So energy flow diagrams. A plant grows. So it grows because of the light energy, it turns it into chemical energy. Eaten by a horse, stays as chemical energy. That kinetic energy is becoming gravitational potential energy as it runs up the hill, and then it becomes kinetic energy again as it falls down the cliff. So light energy, chemical potential, kinetic, gravitational, kinetic. The plane takes a skydiver from the ground into the sky. So that's kinetic energy becoming gravitational potential energy. The skydiver jumps, so the gravitational potential energy becomes kinetic and falls to the ground. Releasing the parachute on the way down, does that make any difference? You've still got the gravitational potential energy becoming kinetic energy. Now what I did was, I said, yeah, a little bit more heat energy is wasted there. But technically the correct answer is this one. Really not much to that second question.